Here's a question that trips up many students. What's the inverse of f of x equals 2x? If you said 1 over 2x, you just made one of the most common mistakes in mathematics. Welcome to this comprehensive guide on inverse functions. An inverse function is like a mathematical undo button. It reverses whatever operation the original function performed. Today, we'll explore what inverse functions really are, how to work with them, and why they're incredibly useful in mathematics and real-world applications. Think of inverse functions like putting on and taking off your shoes. If putting on shoes is our function, then taking them off is the inverse function. The function transforms bare feet into feet with shoes, and the inverse transforms feet with shoes back to bare feet. Mathematically, if a function f takes an input x and produces an output y, then the inverse function, written as f inverse, takes that output y and gives us back the original input x. In other words, f inverse undoes whatever f did. The notation f to the negative 1 does not mean 1 over f. This is crucial to remember. F to the negative 1 of x is the inverse function, while 1 over f of x is the reciprocal. These are completely different mathematical concepts. Inverse functions appear everywhere in mathematics and real life. They're used in temperature conversion, solving equations, cryptography, and even in GPS navigation systems. Understanding inverse functions will give you a powerful tool for solving complex problems and understanding mathematical relationships. An inverse function is one of the most important concepts in mathematics. Think of it as a mathematical undo button that reverses whatever operation the original function performed. The fundamental idea is simple. If a function takes you from point A to point B, then its inverse function takes you back from point B to point A. We can visualize this with function machines. The original function f transforms inputs into outputs, while its inverse, denoted f to the negative 1, reverses this process. Here's how it works. We start with an input x. The function f transforms it into output y. Then the inverse function takes that y and transforms it back to the original x. Mathematically, we express this relationship as f of x equals y if and only if f inverse of y equals x. This bidirectional relationship is the key to understanding inverse functions. Now let's see this concept in action with 3 concrete examples, starting with the simplest case. Example 1, consider the function f of x equals 2x. This function doubles any input value. For example, if we input 3, the function outputs 6. The function doubles the input. To find the inverse, we follow a systematic process. Step 1, replace f of x with y. Step 2, swap x and y. This gives us x equals 2y. Step 3, solve for y by dividing both sides by 2. This gives us y equals x over 2. Therefore, the inverse function is f inverse of x equals x over 2. Notice how this undoes the doubling operation by dividing by 2. We can verify this works. If we start with 6, apply the inverse to get 3, then apply the original function, we get back to 6. Now let's try a slightly more complex example. Example 2, consider f of x equals 3x plus 1. This function multiplies by 3 and then adds 1. For example, f of 2 equals 3 times 2 plus 1, which equals 7. Step 1, replace f of x with y. Step 2, swap x and y to get x equals 3y plus 1. Step 3, solve for y. First, subtract 1 from both sides to get x minus 1 equals 3y. Then divide both sides by 3 to get y equals x minus 1, all over 3. Therefore, the inverse function is f inverse of x equals x minus 1, all over 3. This undoes the original operations in reverse order. Let's try one more example that's slightly more challenging. Example 3, consider f of x equals x minus 2, all over 5. This function subtracts 2 and then divides by 5. For example, f of 12 equals 12 minus 2 over 5, which equals 10 over 5, which equals 2. Step 1, replace f of x with y. Step 2, swap x and y to get x equals y minus 2 all over 5. Step 3, solve for y. First, multiply both sides by 5 to get 5x equals y minus 2. Then add 2 to both sides to get y equals 5x plus 2. Therefore, the inverse function is f inverse of x equals 5x plus 2. Notice how this reverses the original operations. It multiplies by 5 and adds 2. We can verify, starting with 2, the inverse gives us 12, and applying the original function to 12 gives us back 2. In summary, an inverse function undoes the operation of the original function. The key steps are: replace f of x with y, swap x and y, then solve for y. This systematic approach works for any function that has an inverse. Here's a question that trips up many students. Does every function have an inverse? Most people assume the answer is yes, but that's actually incorrect. The truth is, only special types of functions called bijective functions have inverses. A function can only have an inverse if it's bijective. Bijective is a mathematical term that combines two important properties: injective, which means one-to-one, and surjective, which means onto. Understanding these properties is crucial for determining when inverse functions exist. First, let's understand what injective or one-to-one means. An injective function ensures that each input maps to a unique output. In other words, no two different inputs can produce the same output. This is crucial because if two inputs gave the same output, we wouldn't know which input to return when finding the inverse. The horizontal line test is a visual way to check if a function is injective. If any horizontal line intersects the graph more than once, the function is not injective. This is because multiple x values would produce the same y value, violating the one-to-one property. Now let's examine surjective or onto functions. A surjective function means that every element in the codomain is the output for at least one input. In other words, the function covers the entire codomain. No output values are left unused. This ensures that the inverse function will be defined for every value in its domain. Now, let's work through our first example. We'll analyze the function f of x equals 2x plus 1 to determine if it's bijective. We need to check both the injective and surjective properties step by step. First, let's check if this function is injective. For a function to be injective, if f of a equals f of b, then a must equal b. Let's assume f of a equals f of b and see what happens. Substituting our function definition, we get 2a plus 1 equals 2b plus 1. Now we can subtract 1 from both sides to get 2a equals 2b. Finally, dividing both sides by 2, we get a equals b. This proves that if f of a equals f of b, then a must equal b. Therefore, the function is injective. Now let's check if the function is surjective. For any real number y in the codomain, we need to show there exists an x such that f of x equals y. Let's solve 2x plus 1 equals y for x. Subtracting 1 from both sides gives us 2x equals y minus 1. Then dividing by 2, we get x equals y minus 1 over 2. This shows that for any y value, we can always find a corresponding x value. Since f of x equals 2x plus 1 is both injective and surjective, it is bijective. This means the function has an inverse, which we can write as f inverse of x equals x minus 1 over 2. For our second example, let's analyze f of x equals x squared. This is a classic case where the function is not bijective in its natural domain, but we can make it bijective by restricting the domain. Let's first check if this function is injective. We'll test this by seeing if different inputs can produce the same output. Consider f of 2 and f of negative 2. We see that f of 2 equals 4, and f of negative 2 also equals 4. Since two different inputs produce the same output, the function is not injective. This means it fails the horizontal line test. Now let's check if the function is surjective. For f of x equals x squared with domain of all real numbers, the range is all non-negative real numbers. But if our codomain includes negative numbers, then the function is not surjective. Since f of x equals x squared is neither injective nor surjective, it is not bijective, and therefore has no inverse. However, we can fix this by restricting the domain to make it bijective. If we restrict the domain to x greater than or equal to 0, then f of x equals x squared becomes bijective. With this restriction, each non-negative input maps to a unique output, and every non-negative output has exactly one input. For our final example, let's analyze a more complex function. F of x equals x cubed minus 3x. This will test our understanding of bijectivity with a function that has more interesting behavior. Now that we understand what inverse functions are and when they exist, it's time to learn the systematic method for actually finding them. This four-step process will work for any function that has an inverse. Here's our systematic four-step method for finding inverse functions. Each step has a specific purpose and builds on the previous one. Step 1 replaces the function notation with y to make the algebra easier. Step 2 swaps the variables because we want to express the original input in terms of the output. Step 3 solves for y to isolate our new function. Step 4 gives us the final inverse function notation. Our first example is a simple linear function, f of x equals 5x minus 7. This is perfect for learning the method because linear functions always have inverses. Step 1, replace f of x with y. This gives us y equals 5x minus 7. We do this to simplify our notation and make the algebra cleaner. Step 2, swap x and y in the equation. Now we have x equals 5y minus 7. This swap is crucial because we want to express the original input in terms of the output. Step 3, solve for y. First, we add 7 to both sides to get x plus 7 equals 5y. Then we divide both sides by 5 to isolate y. This gives us y equals x plus 7, all divided by 5. Step 4, replace y with f inverse of x. Our final answer is f inverse of x equals x plus 7 divided by 5. This is the inverse function. Example 2 involves a quadratic function, f of x equals x squared plus 3, where x is greater than or equal to 0. The domain restriction is crucial because it makes the function 1-to-1. Step 1, replace f of x with y to get y equals x squared plus 3. Step 2, swap x and y to get x equals y squared plus 3. Step 3, solve for y. First, subtract 3 from both sides to get x minus 3 equals y squared. Then take the square root of both sides. Since our original function had the restriction x greater than or equal to 0, we take only the positive square root. This gives us y equals the square root of x minus 3. Step 4, replace y with f inverse of x. Our answer is f inverse of x equals the square root of x minus 3. Notice that the domain of the inverse is x greater than or equal to 3, which corresponds to the range of the original function. Our final example is a rational function, f of x equals 2x plus 1 divided by x minus 3. Rational functions require more algebraic manipulation, but the same four-step process applies. Step 1, replace f of x with y. Stop x and y. Step 3, solve for y. This requires several algebraic steps. First, multiply both sides by y minus 3 to clear the fraction. Distribute x to get xy minus 3x equals 2y plus 1. Move all terms with y to the left side. Xy minus 2y equals 3x plus 1. Factor out y on the left side. Y times x minus 2 equals 3x plus 1. Finally, divide both sides by x minus 2 to get y equals 3x plus 1 divided by x minus 2. Step 4. Replace y with f inverse of x. Our final answer is f inverse of x equals 3x plus 1 divided by x minus 2. Even with complex rational functions, the four-step method guides us to the correct inverse. The four-step method works for any function that has an inverse. Replace f of x with y, swap the variables, solve for y, and replace y with f inverse of x. With practice, this systematic approach will help you find inverse functions confidently and accurately. One of the most beautiful properties of inverse functions is how they appear graphically. When we graph a function and its inverse together, we discover a perfect symmetry that reveals the deep mathematical relationship between them. The key to understanding inverse function graphs is this special line, y equals x. This line acts like a mirror, and the graph of any inverse function is simply the reflection of the original function across this line. Here's the fundamental principle. If a point with coordinates a, b lies on the graph of function f, then the point with coordinates b, a lies on the graph of the inverse function. Notice how the x and y coordinates simply swap places. Our first example uses the linear function f of x equals 2x plus 1. We'll graph this function, find its inverse, and see the reflection property in action. First, we graph the original function f of x equals 2x plus 1. This is a straight line with slope 2 and y-intercept 1. Let's identify some key points on this function. We have the points -1, -1, then 0, 1, and 1, 3. These points will help us understand the reflection property. The inverse function is f inverse of x equals x minus 1, all divided by 2. Now watch what happens when we graph this inverse function. Notice how the points have transformed. The point 0, 1 on the original function becomes 1, 0 on the inverse. The point 1, 3 becomes 3, 1. The coordinates have swapped, creating a perfect reflection across the line y equals x. These curved arrows show the reflection process. Each point on the original function reflects across the y equals x line to create the corresponding point on the inverse function. Our second example uses the square root function. This will show how the reflection property works with curved functions. not just straight lines. Here's the graph of f of x equals square root of x. Notice how this function curves upward and is only defined for non-negative x values. Key points on this function include 0, 0, then 1, 1, and 4, 2. Let's see how these points reflect to form the inverse function. The inverse of the square root function is f inverse of x equals x squared, but only for x greater than or equal to 0. This restriction ensures the inverse is a function. Watch the reflection in action. The point 4, 2 on the square root function becomes 2, 4 on the inverse. Points that lie on the line y equals x, like 1, 1, remain unchanged because they're their own reflection. This curved arrow shows how the point 4, 2 reflects across the y equals x line to become 2, 4. The reflection property works perfectly even with curved functions. Our final example uses a more complex quadratic function. F of x equals the quantity x minus 1 squared plus 2. This will demonstrate the reflection property with a parabola. Since this is a parabola, we need to restrict the domain to x greater than or equal to 1 to ensure the function is 1 to 1 and has an inverse. Here's the graph of our function, showing only the portion where x is greater than or equal to 1. This creates a 1 to 1 function that has an inverse. Key points on this function include 1, 2 at the vertex, then 2, 3, and 3, 6. Now let's find and graph the inverse function. The inverse function is f inverse of x equals 1 plus the square root of the quantity x minus 2. This function is defined for x greater than or equal to 2. Perfect. The reflection property holds true again. The point 1, 2 becomes 2, 1, the point 2, 3 becomes 3, 2, and the point 3, 6 becomes 6, 3. Every coordinate pair swaps perfectly. These arrows illustrate the reflection process for all 3 points. No matter how complex the function, the reflection across y equals x always produces the correct inverse function graph. The key takeaway is this: the graph of any inverse function is always the reflection of the original function across the line y equals x. This beautiful geometric relationship works for linear functions, curved functions, and even complex functions. It's a universal property that makes graphing inverse functions straightforward once you understand the reflection principle. Understanding the relationship between the domain and range of a function and its inverse is crucial for working with inverse functions effectively. This relationship reveals a beautiful symmetry in mathematics. The fundamental relationship states that the domain of a function becomes the range of its inverse, and the range of a function becomes the domain of its inverse. Mathematically, if function f maps from set A to set B, then its inverse function f inverse maps from set B back to set A. This is why we say the domain and range swap places. For our first example, consider the linear function f of x equals 2x plus 1. This function is defined for all real numbers. The domain of f is all real numbers, since we can input any real number. The range is also all real numbers, since the linear function can output any real value. To find the inverse, we start with y equals 2x plus 1, then swap x and y to get x equals 2y plus 1. Solving for y, we subtract 1 from both sides to get x minus 1 equals 2y. Dividing by 2, we get y equals x minus 1 over 2. Therefore, f inverse of x equals x minus 1 over 2. Notice that the domain of f inverse is all real numbers, which matches the range of the original function f. Similarly, the range of f inverse is all real numbers, matching the domain of f. For our second example, consider f of x equals the square root of x minus 3. This function has a restricted domain because we cannot take the square root of negative numbers. For the square root to be defined, we need x minus 3 to be greater than or equal to 0. This gives us x greater than or equal to 3. So the domain of f is the interval from 3 to infinity. The range is from 0 to infinity, since square root functions always produce non-negative outputs. To find the inverse, we start with y equals square root of x minus 3, then swap variables to get x equals square root of y minus 3. Squaring both sides gives us x squared equals y minus 3. Adding 3 to both sides, we get y equals x squared plus 3. Therefore, f inverse of x equals x squared plus 3, but we must restrict x to be greater than or equal to 0 to maintain the one-to-one property. Notice the beautiful symmetry. The domain of f inverse is 0 to infinity, which exactly matches the range of f. The The range of f inverse is 3 to infinity, which matches the domain of f. For our final example, consider the rational function f of x equals 1 over x minus 2. This function has restrictions due to division by 0. We cannot divide by 0, so x minus 2 cannot equal 0. This means x cannot equal 2. The domain is all real numbers except 2. The range is all real numbers except 0, since the function can never equal 0. To find the inverse, we start with y equals 1 over x minus 2, then swap to get x equals 1 over y minus 2. Multiplying both sides by y minus 2 gives us x times y minus 2 equals 1. Expanding, we get xy minus 2x equals 1. Adding 2x to both sides gives xy equals 1 plus 2x. Dividing by x, we get y equals 1 plus 2x over x. Therefore, f inverse of x equals 2x plus 1 over x. The domain of f inverse is all real numbers except 0, which perfectly matches the range of the original function f. The range of f inverse is all real numbers except 2, matching the domain of f. In every example, we see the same pattern. The domain and range always swap between a function and its inverse. This fundamental relationship helps us understand and work with inverse functions effectively. Now that we understand the theory behind inverse functions, it's time to see them in action. We'll work through 3 examples that show both the mathematical process and real-world applications of inverse functions. Our first example demonstrates the fundamental process with a simple cubic function. We'll find the inverse of f of x equals x cubed. To find the inverse, we follow our standard procedure. First, we replace f of x with y. Next, we swap x and y. This gives us x equals y cubed. Now we solve for y by taking the cube root of both sides. The cube root of x equals y. Finally, we replace y with f inverse of x. Therefore, the inverse function is f inverse of x equals the cube root of x. This demonstrates the basic algebraic process. Now let's see how inverse functions work in a practical, real-world scenario. Our second example involves temperature conversion. The function to convert Celsius to Fahrenheit is f equals 9/5 times c plus 32. We want to find the inverse to convert Fahrenheit back to Celsius. We start by swapping f and c. This gives us c equals 9/5 times f plus 32. Now we solve for f. First, we subtract 32 from both sides. Next, we multiply both sides by 5/9 to isolate f. This is our inverse function for converting Fahrenheit to Celsius. Notice how the inverse undoes the original conversion process. Temperature conversion shows how inverse functions help us reverse real-world processes. Our final example demonstrates inverse functions in finance. Our third example involves compound interest. If we have a function that calculates the final amount after compound interest, we can find its inverse to determine the initial principal needed for a target amount. To find the inverse, we need to solve for p in terms of a. We start by dividing both sides by 1.05 to the power of t. This gives us the inverse function. Given a target amount a and time t, we can calculate the principal p needed. For example, if we want $10,000 after 5 years at 5% annual interest, we would need to invest approximately $7,837 initially. These examples show how inverse functions appear throughout mathematics and real life. They help us reverse processes, solve for unknown inputs, and understand relationships between variables in physics, engineering, computer science, and many other fields. Picture this: you're working on an inverse function problem, and you write f inverse of x equals 1 over f of x. This is one of the most common mistakes students make with inverse functions, and it can completely derail your solution. In this section, we'll explore the most common mistakes students make with inverse functions and provide you with proven strategies to avoid these pitfalls and master inverse functions with confidence. The number 1 mistake is confusing the inverse function f inverse of x with the reciprocal 1 over f of x. These are completely different mathematical concepts. The inverse function undoes the original function, while the reciprocal is simply 1 divided by the function value. Let's see this difference in action with a concrete example. Consider the function f of x equals 2x. The inverse function f inverse of x equals x over 2, while the reciprocal is 1 over 2x. These give completely different results. Let's verify this with a specific value. If we input 4 into our original function, we get f of 4 equals 8. The inverse function should give us back 4 when we input it 8. Let's check. F inverse of 8 equals 8 over 2 equals 4. Perfect. but the reciprocal gives us 1 over 8, which is completely different. Another common mistake occurs when working with exponential and logarithmic functions. Students often lose track of what their variables represent, especially when dealing with the inverse relationship between exponentials and logarithms. Let's work through an example with f of x equals 2 to the power of x. To find the inverse, we replace f of x with y, giving us y equals 2 to the x. Then we swap x and y to get x equals 2 to the y. To solve for y, we take the logarithm base 2 of both sides, giving us y equals log base 2 of x. The third common mistake is failing to properly verify your inverse function. Many students skip this crucial step or do it incorrectly. Remember, if f and g are inverse functions, then f of g of x equals x, and g of f of x equals x for all appropriate values of x. Let's verify our earlier example where f of x equals 2x and f inverse of x equals x over 2. First, we check f of f inverse of x. Substituting, we get f of x over 2, which equals 2 times x over 2, which simplifies to x. Check. Now for f inverse of x, we get f inverse of 2x, which equals 2x over 2, which simplifies to x. Both conditions are satisfied. Now let's discuss proven strategies for success with inverse functions. First, always use the graphing calculator reflection test. The graphs of a function and its inverse should be reflections of each other across the line y equals x. Second, create a systematic verification checklist. Third, practice with different function types to build pattern recognition. Here are some memory aids to help you remember key concepts. Think of inverse functions as mathematical opposites that undo each other. The notation f inverse is not the same as f to the -1 power. When in doubt, always verify your answer using both composition checks. Remember, practice makes perfect, so work through many examples to build your confidence.